Just going to flip the screen. So thanks very much, and so it's a real pleasure to be part of this project and presenting today. What I'm going to talk about is approaches to machine learning, very much from a practice-based perspective, through some of the kind of explorations I've done as a person who is a kind of neural network hacker, computer scientist, and musician. And so I often take the approach of kind of delving quite deep into machine learning models and then going and performing with them. And so I want to share some of my experiences in the hope that they're useful. The scope here really is thinking about machine learning in musical instruments. So I'm really thinking about a real-time approach to machine learning and approaches to real-time manipulation. And I really want to think about how we engage with machine learning as a creative material and think about some techniques that go beyond conventional uses of computer science, uses of machine learning, as Rebecca put it earlier. So the main bulk of this is going through some example applications and trying to thread some lessons through those. And then the last bit is a little listening exercise, thinking about how we train neural networks for sound. So this first bit, I just want to really zoom out and think about what machine learning is. And this is by no means machine learning 101 or anything like that. I know there's a lot of knowledge in the room about ML, but I really want to just think about what's the actual essence of what we do when we engage with machine learning. And I'm going to come back to these themes in the talk. So firstly, we've got a human involved. A human is very, very important in machine learning. That human is face palming because I'm sure we've all had this experience using machine learning that it's really, really difficult to use sometimes, but it's also very, very rewarding, and that's why we persist with it, because there's some magic in there. There's something really amazing that can happen when you get things right, when things align properly. But what else have we got here? We've got some sort of tunable. Actually, let's start from the beginning. The human here has some kind of goal, which might be quite tightly defined, like a typical machine learning task could be to recognize cats or dogs, or to pick out tumors in a CT scan, or try and estimate the health of an ecosystem. So we've got some kind of quite tightly defined goals that people have, but also we might have very loosely defined goals, and especially in creative machine learning. Your goal might be, for example, I want my instrument to sound better. I want it to sound more complicated and interesting, but I don't really know how I'm going to do that. So how do you engage with that process when you've got some really loosely defined goals? So we use machine learning because we don't want to program something directly, because we've got quite a complicated task, and we want to engage it by optimizing something to do this for us without necessarily needing to know how it works. So we've got some sort of tunable model in the middle, and this could be some sort of computational model. It might be statistical. It might be a biologically based model. It could be a lot of things. It could be rat neurons. There's a lot of forms this could take. It could be optics. There's some interesting optical models happening at the moment. And this tunable model is connected to an environment. And this is really important, that these models that we work with rarely exist in isolation. So it's very important to think how they're embedded with what we do. So their inputs, they could be a FFT, it could be a raw audio signal. The outputs could be a video. It could be a sound. That sound could take different forms, different formats in the data. And then going with this, we've got some sort of optimization process. We might call it learning, we might not. We can leave that for another philosophical discussion. But some way of tuning this model to try and get it to do what we want to do. We might not really know what we want to do, but we'll try and send it in that direction. So this is the kind of essence of what I'm trying to approach today. It's also really important to think about how time works in this process. So where is time in this whole thing? It might be stretched. We might spend a lot of time collecting data and then creating a model which runs in real time or non-real time. So we can dilate time like this. We might have this whole process running as part of a performance, so the whole thing is in real time, and then various stages in between. So I'll come back to the real time thing in a bit. It's also important to think as musicians about how time is represented in our machine learning systems. Is time part of the model? Does the model have memory? If it doesn't have memory, then it can't explicitly understand time. Is time represented in the environment around the model? And then so the model has a kind of almost false, maybe I wouldn't say false, but we represent time to the model, but it doesn't know what time is. So that's important to think about. So what I'm going to do is go through a few different example models which explore some different approaches to creative machine learning. And first of all, I want to talk about neural networks as being really interesting sources of modulation. So Rebecca earlier talked about big data and small data is great. I absolutely agree, small data is a really good approach. We can go another step and have no data. So let's think about no data machine learning. And actually, by thinking about no data, we think about what are the intrinsic properties of neural networks, or what can they be, which might be exciting to us. So this comes from an experiment I was doing way back, started my PhD 2008, and it's based on work from Baum and Lexer using these systems called continuous time recurrent neural networks, which are, you can't train them in a conventional way using backpropagation, you have to evolve them. They have really interesting qualities. Without going into too much detail about them, the main thing about these things is they're recurrent. They're like mini feedback systems. And you can optimize them through evolution to do a certain task, or you can just not optimize them and see what comes out. And I got really fascinated about just looking at randomized versions of these models and using them as modulation sources and seeing how they came out. So I'm just going to play some examples. I think I can just move Rebbeca over here, maybe. Is that going to work? Yeah. So these are the outputs of the model. I've really deliberately kept this simple. So we've got this neural network. It's a recurrent network. They get randomized, and I take a couple of the energy levels in the model, map one to the frequency of a sine wave, and the other to the amplitude of the same sine wave. So just for demonstration, this is really, really simple. And what I'm trying to get at here is about the intrinsic dynamics of these models, which to me seem quite musically interesting before you even think about training them. So this first one here, you can start off these models. Sometimes, a lot of the time, you'll just get no sound. So they'll just flatline. Or you might get a little bit of sound like this. Here's an example of another one. So not very interesting. But here's another one that starts to show a little bit of character, you might say. And then this next one coming along, this one starts to have this sense of something interesting going on with it. And then this last one here, I had to stop recording this because it would have just gone on forever. So sometimes these things, they're either kind of flatline or they catch and they start doing interesting stuff. So that one could just go on for a while. So to me, I found this quite fascinating because the intrinsic dynamics of these networks seem to me, when you got lucky, to be quite musical. So why would it be interesting to train them when they're already doing something quite interesting? And maybe the training could be thinking about how these networks engage with their environment around them. So you can think about how they're coupled to the world instead of changing them internally. So this led me on to another form of neural network called echo state networks, which are a bit like these CTRNNs, except they're discrete, and they're a lot easier to train. So you can give them training data and usually get a pretty good result quickly. But again, they have these same kind of interesting intrinsic dynamics. So these networks come from Jaeger, who's also done some other stuff that I've based some work on. So this is a system that I was using as part of Algorave performances, probably 2012-13, using these networks to control concatenative synthesis. And the idea was that the audio signal would go into an echo state network, and then this echo state network would control sources, sections of a corpus, which would then be where a live signal matched from. So it's like live moving around the database, changing the window on the database to see where you pull your matching from. There's a MIDI controller to control this, but also the echo state network added in this interesting modulation to where this stuff got pulled from. And there's also a feedback system which was controllable, so you could send the whole system into this kind of quite interesting behaviors. I'll just play a segment from an example of what that sounded like. So you might be able to hear there's some kind of quite busy stuff going on, which is mainly attributable to the modulation coming from this network. So the point of that really was that it's quite interesting to think about networks and just what's going on inside them before you get to actually thinking about how you're going to train them. And when you do train them, how are you shaping that intrinsic behavior? So to look at the behavior of the network first before you touch it, before you modulate what it's doing. And that can happen by thinking about how the network is coupled with the environment. So that echo state network, in the example I just played, I was modulating how it related to the rest of the world. So how it mapped into choosing sections of the corpus, and how it responded to feedback, and how it responded to audio signals from the sequencer. But the actual network was just random. I tried a few, found one that I liked that has some kind of interesting non-linearities, and just stuck with that and tuned it. So maybe you could say that's a sort of training. It's not an algorithmic training, it's human training. But it's still, well, it's optimization from the human. Further to this, I find it very interesting to think about neural networks as a source of complexity. So and that's something we often need in digital systems. We get complexity for free in acoustic instruments. We have to work hard to introduce it in useful ways in digital systems. And neural networks can, especially time-based ones, can be really good as being sources of complexity in a system. When we pair that with interaction, so we start interacting with these complex modulation sources, then we get into this area called uncontrol, which I think was first defined by Sergei Yorda, and that's talking about the non-linearities and kind of semi-dynamically autonomous behaviors that an instrument might have when you push it into certain zones. And neural networks are a really good way, I think, of trying to shape that uncontrol in instruments, which might be hard to do in other ways. I also really like Stapleton et al.'s concept of co-tuning, where they talk about how the different ways in which we explore parameterized systems, sometimes in kind of raw exploration, but sometimes performatively, with musical gestures. And they think about the different ways in which we engage with these systems to fine-tune them in order to optimize them into interesting musical instruments. So that was no data. Now let's think about data and malleability. So I started doing some experiments with these things called conceptors, which also come from Herbert Jaeger, who's one of the main researchers behind echo state networks. Conceptors are a way of controlling dynamical systems and a way of controlling dynamical systems such that you can teach them to generate signals. And without going into too much detail, I developed a method of sound synthesis using these systems where you could teach a network, we call it concept-controlled recurrent neural network. You could teach one of these systems to generate different fragments of sound. It's a bit like granular synthesis, and then guide this network to create longer pieces of sound in a quite flexible way, so you can do time stretching and pitch control. And the point I'm trying to make here is about malleability. So the learning, the optimization of these systems is fairly straightforward. But what's more interesting, I think, is the way that you can manipulate these networks once you've trained them. So I'll show some examples of how we can do that. So first of all, this is a kind of resynthesis example. So you can teach these to recreate a sound, a sampled sound. So for example, this is a waveform of a kick drum and the reconstruction from the network. Once you've trained the system to make a certain sound, then you can start manipulating this network to do different things. So here's some examples. This is morphing. So this is morphing. There's a model here that's been taught how to do a snare drum sound and a clave sound. And then you can control the morphing between the two sounds by manipulating the neural network. So that's one example. Another is time stretching. So this is a network trained on a 909 kick drum sound, which will do time stretching. So it's increased. Whoa. Let's try that again. So it's increasingly time stretching, you'll hear as we go along. So I'm not really trying to say if that's better quality time stretching than other methods, but the fact is once the neural network can do that, then you can start manipulating the neural network and how it does time stretching. And then, let's have a look at the next example. So this is a drum machine that's built on this method. So you've got 4 channels here. All of these channels, they aren't samples. They're models that have been trained to make certain drum sounds. In fact, 2 drum sounds that you can morph between. And so in this system, if I can find the mouse. There we go. If I just change this down to 8 notes, it takes a long time to render. So you can put in some notes. So you can try this on conceptular.luma.net. And then you can change the way, in quite a lot of detail, about how these sounds morph around and change over time. And then you can hit the render button and see what happens. Now, the frustration with this system is, I'm talking about real-time systems, but it's not real-time, it's well below real-time. And this has been a bit of a bugbear with this system, that I really want to use it as a musical instrument, and it's difficult to engage in that way. So you can have a go at that if you go to that website. So going on from this system, that was a sample-based network. And again, just to remind you, the point I'm trying to make here is that it's an approach of thinking about malleability of networks. So we can train a neural network to do a particular function and then start reaching inside that network and controlling it musically. So this is another example that does pitch control and tone control over oscillators. And it's real overkill. You can do this with analog synth already or a digital synth. But I just found the fact that you're doing it with a neural network is quite interesting. It gives you some extra possibilities. So you can pitch control these oscillators. Here's one that's been trained to recreate a saw wave. So there's a waveform taken from an analog synth. Oh, yeah. So this one here. Maybe that's too sub there. So just train from one waveform, then you can get it to extrapolate, and but kind of interesting things happen. You can see that's not really what you expect from a pitched oscillator, that you get these kind of interesting artifacts once you drive the system a bit too much. So we can move on to a little demo of using these systems for something a little bit more complicated. So this is a model which understands 3 waveforms, and then you can manipulate the model, the way the model works, to change the pitch and to change the tone and to change the enveloping. This is just a kind of simple arpeggio just to demonstrate how this network works. So again, it's overkill because you can do this anyway, but I'm just really interested in doing it with a neural network and the creative possibilities that you get when you do that. And that was quite a vanilla example. So I'm going to move on to something that's a little bit more visual. So this is a technique of video synthesis that uses these same models. And again, the idea is you train something and then you start manipulating it. So this was a piece that was presented at Seeing Sound 2018, I think. And what this does is you train a hive of neural networks to recreate a video, a very short loop of video. And instead of thinking about video as a set of images that come after each other, you think about each pixel over time. And so each pixel has a brightness timeline that you can see in the bottom left, right corner there. And so what I did was train a hive of neural networks to learn the brightness of all these pixels. So we've got 100 by 100 video here, so it's really, really low quality. But then there's 10,000 neural networks, tiny little neural networks in a hive together that have learned how to control each pixel to produce this brightness. And let's see the resulting video somewhere. So here we go. And what you can do, so this was a live system, an audiovisual piece, and as you play back the video, you can start manipulating the way the neural networks relate to each other. So they they kind of bleed into each other and leak into each other and change the behavior of their neighbors, which propagates over the video. So in a way, you get this complex system. So let's just have a look at some of the stuff this does. So it's a little... Sometimes you can see the original image. Sometimes you get everything saturates away, and you get these complex behaviors between the pixels. Maybe just skip around. I shouldn't have chosen red, because it doesn't come out very good on projectors. So the point here is training a neural network to do a specific task, but then manipulating it afterwards. So thinking about malleability. Just trying to move the slides on. There we go. Sorry, it just crashed. Oh, there we go. Right, working again. There's a wider research area around this, which we can call, there's two topics really, hybridity and network bending. And this is coming from colleagues on the Mimic project, which I'll talk about in a second. And hybridity is really about thinking about how can we manipulate already trained networks architecturally. So we can think of a kind of Frankenstein model of training a network to do a certain thing, then taking the half of one network and mixing it with half of another network and seeing what happens. So it's an explorative approach to being creative with machine learning and thinking about how we can get exciting results by some sort of process of recombining different bits of trained network. We've also got network bending, which is what I've been showing you really, which is thinking about how we can manipulate already trained neural networks. So we're not manipulating through optimization, we're manipulating in real time. So for example, thinking about what if I take one of these neurons and suppress it, stop it working, what will happen to the output of the network? There's some also really interesting work going on by Terence Broad in the audiovisual domain about this expressive manipulation of neural networks. So I think it's a really interesting research area at the moment. So next I'm going to think about, having thought about malleability and how we can engage with pre-trained models, think about how we engage with training models and think about timescales involved in that. So I'm a co-I on this thing called the Mimic project, which is about music and machine intelligence. We probably share quite a few goals with the FluCoMa project. And so this is being run between University of Sussex and Durham and Goldsmiths and UAL in London. There's a website you can go to which has lots of interesting JavaScript tools on it. As part of that project, our team at Sussex, so myself, Thor Magnusson and Francisco Bernardo, are working on how we engage with machine learning through live coding. So Rebecca already talked about some of the issues around how we engage through programming, and we're exploring how we can think about usable ways to code to engage with machine learning. Part of our solution is to think about how you can design languages. So we've got a language design tool called Semma, which runs on the web. And with Semma, you can kind of get quite deep into making your own customized languages for live coding and get them to engage with machine learning processes in the browser. And I wanted to highlight one bit of research that we've been doing recently, which is about designing customized languages which kind of hide the big mess that goes on behind machine learning. So we think a lot of the problems that we have in creative AI are because a lot of stuff happens in Python notebooks or in MATLAB, and we're trying to think about how you can bring that out of the science lab into the hands of musicians who and give them kind of easier, well, not necessarily easier, but more constructive interfaces that are more relevant to their creative needs. And in particular, this language here, so I'll just move over to Chrome. This is called rubber gosling, partly because it's kind of inherited from this old, you might remember a 90s sequencer called a rubber duck, which is like a little ACID 303 sequencer. So we made a live coded version of that, and then a machine learning version of that, which we call rubber gosling. And you can go to sema.codes, and you can try this out. There's a tutorial called a machine learning powered sequencer, which has all of this. The way this works is it's got reinforcement learning running in the background. And so there's an agent which listens to one source sound and one target sound and tries to learn the relationship between them. So for example, you could play a kick drum as the source sound and then ask it to learn the hi-hat pattern. And then you can put it in prediction mode and it will try and repeat that hi-hat pattern in response to the kick drum pattern. So there's reinforcement learning going on in the background. I think the particular innovation of this system here, that it's a performative system. Everything is enclosed in this language here. So I'm not going to demo it right now because it might take a little bit of time to get something useful out of it. And also, I'd be quite happy to submit that I haven't practiced this for a while, and you need to practice it. It's a performative system. So I'll kind of concede that to make that point. That it turns the training of the neural network into a performance. It's a real-time, the training is now a musical instrument. So what would happen is that you'd be running a sequence and say, I'd type learn here, so I'd get my snare pattern to be associated with this kick pattern, and then I'd put this into predict mode, and hopefully the snare would kind of follow what you taught it to do in response to the kick. But then when you did different things with the kick, you get some interesting stuff happen. Maybe that we talk about serendipity and creative discovery that through areas that the network hasn't learnt by. But the important thing is that everything's embedded in this language, and it's a performance, even down to the way that you have to watch the training error come down as you're showing it examples, and kind of stop training at just the right moment so you don't overtrain or undertrain the system. So that's a system with the training process embedded into it. And the next avenue that I'm exploring in research at the moment is how do we take this the next step and embed machine learning right into the instrument? Because I think that's a really important thing to do. So there's some kind of layers of computation here. We've got a GPU farm, we've got a laptop, and then we've got some microcontrollers. I think there's something of particular value of not having your instrument umbilicaled to a lot of processing. I think there's something about the embodied experience that you'd get from having machine learning embedded in your musical instrument that would give extra value to the way that you train machine learning. So this is really what I'm thinking about at the moment, trying to get away from the laptop. The Arduino is great, but it's not powerful enough for what we want to do. So I'm looking at these. This one on the right-hand side is an FPGA, a field programmable gate array, which is a reconfigurable computing system. The advantage of these is they're super fast. so you can do real-time audio processing with them. Disadvantage is they're just a bunch of logic gates, so they're quite difficult to use. You have to program them in this weird programming language called Verilog, which is really tricky. So this research is being presented in a couple of weeks at the AI and Musical Creativity conference, but I'll just kind of roughly summarize what it's about, really. So the idea is, my question is, are numbers an expensive abstraction? So this is about trying to get machine learning really, really super efficient. So it's a very functional thing, but the result of that would be to be able to embed it straight in instruments and have this embodied experience of training and exploiting neural networks. So these new networks, they're called SLOW, which stands for Stochastic Logic Optimization, and they run without numbers. So they're really, really super efficient. They're just states on and off. And by configuring logic gates together, you can train these networks of logic gates to perform interesting functions. So you can train a neural network to and put it right in an FPGA, put it inside an instrument. So this is really early research at the moment, but the early results are really good. So so far, I've trained these things to do beat prediction tasks, and in comparison to standard methods which you'd use for this, like genetic algorithms, they outperform them. So it's looking promising, but you think, well, this is just logic. How do I get waveforms out of them? So you can take an approach which uses reservoirs and use them for waveform generation. So this thing at the top looks like a spectrogram, but it's actually the activations of all the binary nodes in a network, which is running in a kind of recurrent way using feedback. And you can train this reservoir, this system, it's a random Boolean network, to behave in a certain way and extract signals out of it. So there's some really promising stuff here, but there's a lot of work to do with it. So I'm just going to summarize what I've been talking about so far and then move on to a last section, which is a listening exercise. So I think it's important to think about how we engage with machine learning creatively. The standard computer science perspective, as Rebecca's already talked about, we might say it's about model production, really. So we put a lot of effort into training, and we get a model that works hopefully really well. In creative machine learning, we might not necessarily be so interested in this production of a hopefully near-perfect model. It's perhaps more interesting to engage with the process as a whole. So think about how we can engage performatively and creatively with optimization as well as the final output. And also think about what we can do in manipulating models that have been trained. So how can we use network bending or hybridity to take these models and mismatch them to other models, or try and reach around in the internals of what's going on and get some creative results. And there's some huge research challenges here, thinking about these networks are all essentially very complex systems, so thinking about how to interfere with these models in musically interesting ways, how to hack them about. So we need to think about kind of very guided hacking. Neural networks are Class A producers of complexity and uncontrol. So when as we saw with the CTRNNs at the start, they can be really, really good modulation sources, and we can get some quite interesting and sometimes what might seem like musical signals out of them. And we can train them, or we can take a no data approach and instead fine-tune how these models are related to their environment and how they interact with their environment, rather than actually training them. So this is very much human optimization rather than algorithmic optimization. And when we have these networks in interactive systems, we can think about how can they give us interactive complexity and uncontrolled. How can we use them in an instrument to generate musically interesting, non-linear dynamics that we wouldn't really get if we wouldn't use them? And of course, there are lots of different ways you can make non-linear dynamics. You could, if we use statistics, we can use randomness, we can use all sorts of processes. But I think just kind of experientially, I just found so much interesting surprise that's come out of neural networks compared to other methods. I'm not trying to say they're better or not, but just from personal experience. And this is where it comes into serendipity. So I think neural networks are very good serendipity machines. They're very frustrating to use, and they often come out with the wrong results. But when they often increase the chance of something musically interesting happening in your system. And so that's one of the pleasures and the kind of magic of using these things when it happens. And the research question here is, how do we increase the chance of serendipitous happenings? And that's to do with how we tune these networks into the environment surrounding them and the kind of networks that we use, and also thinking about strategies. So Rebbeca was talking about Letitia Tsunami's strategies earlier, about how she trained different networks and introduced them into the instrument. And maybe this is about increasing the potential for serendipity. And lastly, we can get some really musically interesting results by thinking about malleability of models, as demonstrated by the conceptors. So this is we've got 5 more minutes?
Yeah, we thought it was right. Let's do that,
Yeah? Okay. So this is a listening exercise. I got really interested a couple of years ago with what was going on with a neural network when you train it, and how does it sound, and what's the point where perceptually we understand, or the network's doing what we want to do. So this is an example from a variational autoencoder, and what it's doing is being given a sound, and it's just trying to reconstruct the same sound. It's being given the spectrum, the FFT, and it's being condensed down to a kind of feature, reconstructed again. And what I did was I recorded the reconstruction at every point in the training process. And this became part of a live performance. I had a corpus of these and kind of crossfaded through them, so I made a little instrument out of it. But also, I'm really interested in how neural networks generalize. So often we're training a neural network. When do you stop training? If you train too much, you're going to overfit a network, and it's not going to be flexible. If you undertrain it, it's probably not going to do what you want it to do. So where do we stop? And that might be obvious for scientific purposes, but for creative purposes, what's the right answer to that? So let's have a listen to this final example. Here we go. This is going to start loud, but then it'll go quiet again. So this is about a minute long, and it's just in repetitions of what happens when you train this network. And when we're listening to it, I want you to think about what's the point at which you start to recognize the characteristics of the sounds that it was trained with, which I'll play to you in just a second. And also, what's the point when we actually think it's doing the job, it's recreating it properly? Maybe those are two separate things. So first of all, this is the original sample. It's a little loop that was made with the Moog DFAM. Let's turn it up. Is that all right? Let's play it once more. So a little analog drum loop. And here's the neural network trying to recreate it. And after we listened, I'll show you the loss graph. So think about how far along it was when you felt like it was doing the characteristics of the original sound. let's just go back to here. So this is the loss graph of how this thing was training. And I don't know what anyone else thinks, but to me, maybe around here, it starts to pick out the characteristics of what's going on. Everyone's nodding in agreement. But here it probably sounds more like the original. But it's before it's actually officially minimized its error that we actually get the characteristics of this sound. So that's just an open question. I don't know what conclusions to draw from it, but just that we should really think about what's going on inside our neural networks. And that's connected to this no data thing as well, thinking about the intrinsic dynamics of what's happening in these models that we use before we engage with them. So that's all I've got to say. Thank you.